Hello, welcome to my channel. In this video, we are going to be taking a look at the physics behind rocket propulsion. So in this video, we start by assuming that when a rocket is launched into outer space, right, we have that particular rocket is assumed to move in a frictionless environment, right? Because in outer space, there are no gases, so it moves in a frictionless environment. And when the engine is switched off, that particular rocket can still continue to move at a constant speed. So we'll start from that assumption that this rocket is already moving. It has a mass of m plus change in m, where this m is the mass of the empty rocket without the fuel, while this change in mass is the amount of fuel inside the rocket. And it is moving at a constant speed in this direction, right? So as long as there are no air resistance around the rocket, this particular rocket can continue to move at a constant speed, right? Even when the engine is switched off. Then the momentum of this particular rocket at this point in time where we are starting our assumption from is giving us Pi, which is the initial momentum, the change in mass plus m times this v. So let's now consider another instance where the engine is switched on, probably to increase the speed. We have this one. So as the engine is switched on, this particular gas will start coming out of this exhaust, and we have the new mass, right, which is m, because this new mass of the fuel is being used up. So we have m and a new velocity, which is v, plus another extra change in v, right? And the momentum is giving us, we also have the change in mass, right, being coming, which is the exhaust gas coming out of the nozzle. Then we also have the speed of this gas is giving us ve, so we'll call it the velocity of the exhaust velocity. Then the momentum will definitely be giving us our m times this particular one, right? And this particular one and this one. So we'll consider all of them together. Now let's define the new parameters that we have. Our VE is defined as the speed of the exhaust. We also have that the velocity with which the gas leaves the nozzle, also known as burnout, is the V here, which is this V minus the velocity of the exhaust. Because this one moves in this direction, this one moves in this direction. So the relative velocity, right, of the burnout is given by V minus VE. Okay, so let's consider for an isolated system. We can see that it's just only these rockets. It is not interacting with any other object or any other rockets. It's just only it. So we say it's for an isolated system. So the momentum, change in momentum, will always be equal to 0. That means the P initial momentum must be equal to final momentum. Okay, so we have our initial momentum is given by this, which is this times this. So let's check out the final momentum. The final momentum is given as the change in mass times this relative velocity plus this mass times this velocity, right? So you can see that the combination of this momentum and this one gives us the final momentum. So if we equate this one to this, we should have this one times v, which is the initial, equal to the final. Then we can expand this expression and we get this times this, this times this, equal to this times this, this times this. Then this mass times this velocity plus this mass times change in velocity. So if we notice, we can cancel out some of these parameters, this, and will result to this equal to this. So at this point, we make an assumption that as we move from change in t tends towards 0, then change in m will become dm and change in v becomes dv. So we also have that this particular expression, right, will be equal to this, because this change in m becomes dm and this change in v becomes dv. So the next is to say, okay, the increase in the exhaust mass, dm, results to a decrease in the mass of the rocket, dm. Hence, we have dm equal to minus dm. What that means is that as our small dm increases, as the amount of the gases that comes out increases, then there will be decrease in this particular one, which is change in m, right? So because this one will be reducing, right, which means the change in m equal to this change in m. So if you notice, this particular one will be increasing and this one will be reducing. And because this one will be reducing, the change in this one, if you multiply negative to it, it becomes positive. So we have this one equal to this particular expression. We can also look at it this way, that let's imagine that this initial mass is 10 kg. So if you remove 1 from it, this one will reduce to 9. And the final mass here will now be 9 kg minus 10 kg, which will be equal to what? Minus 1 kg. If you check this one, let's assume that the 1 kg has come out of it. So if you notice, 1 kg, which is the final mass, minus 0, which was the initial mass, will be 1 kg. So if you notice, 1 minus 0 will give us 1. Then this one, 9 minus 10, will give us minus 1. So this minus here makes it positive. So that's why this one will be equal to this particular expression. So let's also consider that our dm will now be equal to minus dm, right, from the assumption that we've made. So anywhere we see dm, we'll replace with minus dm. So we recall that this expression equal to this. After we cancelled some of those parameters from the momentum, after we equated the momentum, right, we got this particular expression equal to this. So at this point, we can replace dm with capital letter dm. So we have m dv equal to this equal to minus ve dm. So we replace this one with minus dm. Now we just need this part and this part. So we have m dv equal to minus ve dm. So at this point, we can separate the variables, and we have dv equal to minus ve dm all over m. And by the time we integrate both sides, right, we have dv starting from this point, right, to this point, initial velocity to the final velocity. Those are the limits. Then equal to minus ve, because it's a constant, we can bring it out. Then we integrate this one from initial mass to final mass. So if we integrate this one, we have vf minus vi, right, equal to minus ve. If we integrate this part, it gives us ln m, and that ln m will put in the final mass, initial mass. Okay, at this point, we can send minus in, so that it becomes vf minus vei equal to ve. Then these two will change. So it becomes mi minus mf, right? So from our law of the laws involving logarithm and ln, we notice that this expression can be written as this expression here. So m all over mf, right? And that's it. This is now the formula for solving problems under rocket propulsion. So let's analyze this particular formula. We notice that when the rocket is initially at rest, this part will become 0. But if it possesses a particular initial velocity, we can put it here and use it to calculate the final velocity when the rocket's engine is put on. Also, we notice that the final velocity will increase as long as this exhaust velocity increases, right? Also, from this point, we notice that if this one is greater than this, everything will be a positive value. And that means that it is important that for us to have high velocity, that's high final velocity, the initial mass must be greater than the final mass. Our initial mass here is the mass of the rockets plus the fuel, while this mf is the mass of the rockets without the fuel, because the fuel is being used up. So it is important for us to have mi greater than mf, so that if you design your rocket, make sure that your final mass is less than the initial mass. Okay, so at the end of the day, we move on to the next stage. If we recall from this formula, this one here, so we notice that we can make our divide both side by t, and we have this expression. So what we have here is now mass times acceleration equal to minus the exhaust velocity times change in mass with respect to time. So we also have that our m dv dt equal to, if we take the positive of this one, which gives us this expression is equal to the thrust of the rocket. The thrust coming out of what? The rocket. So we notice that the higher the mass, the higher the thrust. Or the higher the exhaust, the higher the thrust. So if you want more thrust, you increase the rate at which this exhaust, the velocity of the exhaust, which means the rate at which the gas comes out of the what? The nozzles. Okay, so let's solve one or two problems under this question. So we have the first question. A rocket is fired in deep space where gravity is negligible. If the rocket has an initial mass of 6,000 kg and ejects gas at a relative velocity of magnitude this, how much gas must it eject in the first second to have an initial acceleration of this? So now we're talking about acceleration and we're talking about exhaust. There is nothing like final velocity in this case. So the formula we are going to make use of is that of the thrust. So we recall that thrust equal to this expression, right? And since we know our acceleration to be this, then that can be the acceleration. Then we know our mass, initial mass, right? Then we can calculate, we already know our exhaust velocity. Then we can calculate how much gas must it eject in the first second. We can calculate this one. Then at that point, we have MA, this one becomes A equal to this. We make VE the survey formula, and we make dm dt the survey formula, right? And that gives us dm dt. M is 6,000 times 25 all over the exhaust velocity, which is given here, relative velocity of the magnitude this. And at the end, we have dm dt equal to 75 kg per second. So this is the amount of gas that comes out of the nozzle per second. And that's it. So let's check another question where we have a rocket is in free space and has a total mass of this, of which 3.4 times 10 raised to power 5 kg is fuel. If the velocity of the exhaust gas is this, when the rocket engine is fired, what is the final velocity of the rocket at burnout? So at this point, we're talking about the final velocity. We have the exhaust, we have the initial mass. So we recall that this formula will be used. So we're asked to look for this. Initially, it's stationary, or just the initial velocity is not given. So we assume that it's stationary. So it's 0. We already know the exhaust velocity, which is 2,000. We know the initial mass, which is this, of which this is fuel. So what we notice is that the MF, the final mass, will be this minus this to give us MF. So let's look at the parameters given. VE equal to 2,000 meters per second. The initial mass is this, which is this. The mass of the fuel is this. But we need mass, the final mass of the rocket. So we have MF equal to 4 minus this. That's this expression minus this. That will give us 0.6 times 10 raised to power 5 kg. So if we substitute all this into this formula, we should have VF equal minus 0 equal to 2,000 ln this expression. So we'll go ahead to calculate this expression, and we end up with VF equal to 3,794. So one would expect that the final speed will be greater than the exhaust speed, right? So that's it. I hope this helps. Please like, share, and subscribe. Thank you.